Hello everyone, welcome to today's class. And today's class is on topic of human eye and colorful world. So in today's class we are mainly going to focus on four main topics. So one is human eye and its defects. The second topic that we will discuss in today's class will be refraction of light in prism, and the third one will be dispersion of light, and lastly we will talk about scattering of light in today's class. Okay, so let's start with human eye. So without going into deep into the structural geometrical or sorry physical structure of human eye, just let me tell about the working principle of it, how it actually works. So mainly to know about the working principle, just we have to know about basic structure of human eye. So mainly there are lot more parts associated with the human eye, so we are only interested about the lens and the retina. Okay, so lens that works as a focusing element of light, and the retina is your screen where the image is created. Now when light incident on the lens, it actually focuses the light on the retina, and there are lots of light sensing cell like rod cell or cone cell, this type of cells present on the retina, and they actually receive the light and creates an electrical impulse or electrical signal that is transmitted via this optical nerve to the to our human brain. Okay, so mainly main function of this retina is to create an image, and that is obviously a real image, and it is an inverted image. Okay, that's how our eye actually works. Okay, so there is a twist. So twist is that our eye, that is the focus, the lens, that the focus of the focal length of this lens is not a fixed value, that doesn't has a fixed value, rather it can vary. Okay, so there is a muscle called ciliary muscle which is connected here, actually that is connected here and here. So this ciliary muscle actually uh, has a big role in changing the focal length of the lens of our human eye. Okay, so how does it work? Just let me explain it briefly. So we are talking about the ciliary muscle and the lens of our eyes. So mainly the lens of human eye is full of some fluid, and refractive sorry actually the focal length is mainly depend on the curvature of the lens. So ciliary muscle, what it does is it actually change the curvature of the lens. That means this two muscle actually can extend this thing or contract this thing. So when this lens actually extended, it becomes thinner, and as a result its focal length actually changes. Okay, or mainly it increases, and when this ciliary muscle actually contracts, it become this lens actually becomes thicker, and its focal length actually decreases. So that's how it changes the focal length of the lens. Ciliary muscle actually changes the focal length of the lens of the human eye, and it actually some kind of it actually helps us to see the distant object, or sometimes it actually, this modification in focal length actually helps us to see distant objects, and sometimes when the object is placed at very close to our eye. Okay, so this two different thing happens in two different condition. When the object is at very close proximity of our eyes, then this contraction of the ciliary muscle happens, and the focal length has some kind of changed. And then when we see at any distant object, then again the extension of the ciliary muscle happens, and accordingly the focal length of the lens changed. Okay, so that means that this change in focal length actually help you to see the object for a different position when it is very close, but when it is at a very distance, far away from your eyes. Okay, but there is a limitation of working of this ciliary muscle, and it can't contract too much, or it can't change the focal length of your lens uh, on a big note. So there is a limitation. So there is a limitation of our eye. So what is that? That is, there is a near point that is 25 centimeter for human eye. That means this is called near point of human eye. And what is this? This is sometimes called minimum distance or least distance for distinct vision. That means when you put any object at 25 centimeter, you can see it clearly, but if you put it at 20 centimeter or 15 centimeter, you will not able to see it clearly. Okay, so that is the significance of the near point. So that is mainly due to the limitation of the ciliary muscle, or due to the limitation of the working of this of our eye lens. But main fact is that the main point that I want to highlight here is that the focal length of our eyes can be changed, and it is changing according the condition, according to purpose of seeing. So, okay, so that is a big thing for human eye. And for any practical lens made of solid like glass, we can't never expect this kind of phenomena. But for human eye, that is a phenomena that actually helps us to see a distant object and as well as a closer object with the same lens there. Okay, fine. And this change in focal length is called accommodation of eye. Okay, so this was the brief about a human eye, and main important key point about the human eye. Another thing that we can I can mention it to you, that is the position of our human eye. They are placed side by side, and so that actually provides us a good or a large horizontal view, or a lateral view, in compared to the vertical or the longitudinal, sorry, that provides us a large longitudinal range of view or a horizontal view, in comparison to the vertical or long lateral view. Okay, so that's the reason why the TV screen are always comes in rectangular shape, where the length of the screen is bigger than the breadth or the height of the screen. Okay, so that is mainly due to the position of our two eyes. Okay, so that's the thing. Now let's talk about some defects of a human eye. So first thing is that the first effect is the myopia, that sometimes called as the nearsightedness or short-sightedness. That is actually your short-sightedness. So that means our eye is very much comfortable to see any object which is close to our eyes, but it is facing some difficulties when we are seeing some distant object. Okay, so what happens, so let me draw a simple diagram. So when we are talking about a distant object, that means the rays are coming from that object are mainly parallel. So in myopia, this parallel rays of light actually, they are, this lens is a convex lens or converging lens. So it has the property to converge the parallel rays. So in myopia or in the short-sightedness condition, this there is a change in this lens of our eyes, such that it actually focuses this rays very close to it. That means this rays are not focused on the retina, rather it focuses close to the eye. Okay, so that means when this rays reaches to the retina, instead of creating a sharp image, they create a blur image. Okay, so that is the problem uh, with the myopia. Okay, so that means this is actually due to converging the light in front of the retina. Okay, so that is due to this fact. Now how we can correct this thing? So we can so thing is that this lights are being focused in front of the retina, so we have to put this image on the retina. That means we have to do something so that this lens of our eye, after making these rays converge, it will create an image on the retina. So how can do that? Just place a concave lens in front of the eye. Okay, so this concave lens will diverge some amount of rays. Okay, so the rays will be diverged, and since these rays are diverged, so there will be some difficulties to make them converge. So for the parallel rays, this lens actually converging the rays in front of the retina. Since now the rays are diverging, and this divergence of rays is actually accomplished by using this concave lens. So now the lens will face some amount of difficulties in converging the rays. So now this image will be formed on the retina exactly. So there will be a sharp image on the retina now. So that is the uh, actually correctness, or that the correct that can that's how we can correct this myopia condition. Okay, so that is the correction that we can actually provide for myopia. Okay, so this kind of change in lens condition can be of uh, due to of maybe excessive curvature of the eye lens. Okay, or maybe due to the elongation of the eyeball. So that may be the reason for this thing. Now the next defect in human eye is hypermetropia, or that can be say as a long sightedness. So let's talk about the hypermetropia. So that is long sightedness, and in this condition, uh, the man can able to see an object which is far away from him or her, but a close object is not clearly visible for him. Okay, again one thing, these diagrams be can look funny, but this is a simple diagram that you can draw in your exam hall, or anywhere. Okay, so you don't need to make a good or maybe exact diagram of eye, but that is good. We just want the lens and retina to show what is going to happen or what is happening, and we are good to go with that. Okay, so hypermetropia is long sightedness where a patient or a man can able to see the distant object, but he or she is not able to see a closer object clearly. Okay, so why this happens? This is again due to some kind of changes um, in this eye lens. Okay, so or maybe in the ciliary muscle, so that any kind of uh, problem can be happen. So what happens for this hypermetropia condition? When an object is placed very close to human eye, so that means for a closer object, we always know that for a closer object or a object at a finite distance, the rays of light that comes from the object are always a diverging rays. Okay, so that means the rays those are coming from the closer object are diverging rays, and this lens of our eye now is unable to converge them on the retina. So that means again the these rays are not completely converged on the retina. So that means here elongated image is formed, or a blur image. Here your object is a point object, but here the image is has a larger shape. That means it has some amount of elongation, and also it will be blur. Okay, so the image will be blurred. So that is problem with the hypermetropia condition. Okay, so now what is the correction that we can provide? Now here you can understand your lens is facing some problem in converging the rays. It is not able to converge the diverging rays within this short distance. Okay, so now we have to put some mechanism so that our lens, that means the lens of our eye, can converge these diverging rays. So the solution for this is just put another converging rays or convex lens in front of your eyes. So what will this lens do? This lens will do a partial convergence on this diverging rays. That means this lens will converge these diverging rays partially, and rest of the function will be done by your eye lens. Okay, lens of your eye. Okay, so that means this thing is your spectacles. Okay, so this convex lens will provide some amount of convergence to these rays. Okay, and the rest of the convergence will be provided by your eye lens. Okay, so there will be a sharp image on the retina again. Okay, so that is the correction for the hypermetropia condition. Okay, and the third one, that is the presbyopia condition. Now this myopia and hypermetropia, these two condition mainly can happen with any uncertain or unhappening things. Okay, like some kind of stress or stress in eye that can be a cause for the myopia or hypermetropia. Okay, so some unhappening things will is happens to when it happens to your eyes, then it actually causes the myopia or hypermetropia. It doesn't have direct relation with your aging, but it is related to the some unwanted things, like stress on your eyes. That means when you are continuously using smartphones or laptop, or you are under a high beam of light, so this amount of light actually put some amount of stress in your eye, and that's how this things happens to your eye. But what is presbyopia? Presbyopia has a direct relation with aging. Okay, so this is directly related with your aging. That means when actually the functioning of eye actually controlled, that means accommodation of power, that means power accommodation. That term already I discussed is the accommodation of human eye. That means the power accommodation of human eye, that is actually controlled by the ciliary muscle. Okay, so with the aging, actually this functionality or the elasticity of the ciliary muscle actually changes, and it becomes stiff. Okay, so that's why this complete power accommodation of human eye is actually deteriorated, or actually it becomes fainted, or it becomes not that much, or it doesn't do that much better with the aging. Okay, so that means with aging uh, we face actually some problem with the vision, like we can have short sightedness, we can have the long sightedness, or we can have the both. Okay, so this is the thing that is the presbyopia. Okay, so that means we already learn about myopia, hypermetropia, and presbyopia. The myopia and hypermetropia, these two things are not directly related with the aging, and the presbyopia is directly related with the aging. So myopia and hypermetropia has direct relation with the stress that we are putting continuously on our eye. Okay, so that thing, that one note that you have to keep in your mind always, we have to give your our eye a proper rest, and continuous use of smartphone or high beam of light or laptop is not good for your eye. Okay, so next topic that we are going to learn is the refraction of light through a prism. So you know about the prism, that is a geometrical structure, and that has this tent like structure. Okay, so prism, we will actually talk about glass prism, that means a prism made of glass. So that has a structure like this, that is a straight tent like structure. So we can see there is actually five faces: this one, this below one, and this one, the front one, and this one. Okay, there is a total five sides. Three of them are triangular in shape, and rest of sorry, two of them are triangular in shape, and rest three of them are in rectangular shape. Okay, so the surface on which the prism is placed over the ground, that means this side is called the base. Okay, this one is called base, and the rest of the two sides, rest of the two rectangular sides, are called the refracting sides. That means this one and this one, these two sides are called the refracting side. So this one and this one is called refracting side, refracting faces. Sorry, not side, this is a refracting faces. Okay, and this triangular face is called principal section. Okay, this triangular face is called principal section. Now after that thing, means we will continue with this principal section. That means we are not always going to draw this whole tent like structure. We will draw this principal section only. Okay, so for this principal section, the right one and the left one is your refracting face, and the bottom one is your base. So here also this one is your base, and this one and this one are your refracting surface. Okay, so what happens with that refracting surface? Light can incident on any of them and can emergent from other face. Okay, so if one light incident on this face, that will emerge from this surface. Okay, so that is the main idea about the prism, glass prism, simple glass prism. And one thing you have to keep in mind, that angle, this top angle, that is called angle of prism. Okay, that is called angle of prism. Now we are going to learn about the refraction in a prism. Okay, so now take a ray of light that is incident on the first surface with an angle I. Okay, so this is your normal. Okay, and that is n prime. Okay, this is the normal on this surface, and this is your incident ray, and the incident ray makes an angle I with the normal. So this surface is your incident surface, and so you can expect the light to come out from this surface. Okay, so since we are assuming this surrounding is here, and this thing is made of glass, so glass is denser compared to the rarer, so we can expect a bending of light towards the normal. So light should travel uh, in that direction, in this direction, okay. But since this glass prism is present, so it will refract it towards the normal, so it will get some deviation, so it will go like this, okay. So it should go like this. Since this prism is present, so light will move towards the normal and it will go like this. So this angle is angle of refraction, okay, on the first surface, and that can be represented as r1, okay. Now this light rays is incident on the second surface, that is the interface between glass and the air, with an angle. Let me draw the normal on this surface. Let this is the normal on this surface, let it is m prime, and this is the angle of incidence for this interface, and that is, let it is r2, okay. So now light is going from glass to air. Here also there is air, so that means light is going from denser medium to rarer medium, so it is expected to go away from the normal, so it will go like this, okay. So if you take a look on the total path of the light, if this prism was not there, so then light would go in this path. That means, that is, let p q h, okay. So it would go through a path p q h. Since this prism is present, light has gone through this path r s, okay. So that means there is a so light would go like this, but now light is going like this, so that means there is a deviation or angular deviation. That means there is a change in direction of propagation of light, and the total amount of angle that the light has changed its direction is this, that much. It was going in that direction, now it is going in this direction, so this angle is called angle of deviation d, okay. So d is your angle of deviation. So what is angle of deviation? So angle of deviation is the angle between the incident ray and the emerging ray. This ray is your emerging ray, okay. This ray is your emerging ray, okay, fine. So this is the all about the refraction in glass, in refraction of light in the prism. So next topic of discussion is our dispersion of light. So before starting the dispersion of light, let's just uh, mention some equation associated with the refraction of light, that is Snell's law of refraction. That actually says sine of I divided by sine of R, that means sine of angle of incidence to the ratio of sine of angle of incidence to the ratio of sine of angle of refraction is constant, and that is actually known as 1 mu 2, that is the refractive index of medium 2 with respect to the medium 1. Now as we know from our previous knowledge, this term mu is actually called the refractive index of the medium, and it is a constant. But now I am going to say you something, this is not a constant term, rather it depends on the wavelength of light, okay. So this mu is not a constant, rather it depends on the wavelength of light, like a formula A plus B by lambda, okay, plus C by lambda square, where lambda is the wavelength of light used. So that is your wavelength of light, okay. So that means you can expect, if wavelength of light differs, that means the refractive index of the medium also changes. That means a medium that actually showing a refractive index 1.5 to a uh, red light, that can show a different refractive index, maybe 1.5 to a violet light. Okay, that means the if you employ different color of light, the refractive index of the medium will change. Okay, and that is actually whole idea behind the dispersion of light. So here we have to know about another thing. One thing is monochromatic light, another thing is polychromatic light. One is monochromatic light and second one is polychromatic light. What is monochromatic light? Monochromatic light is a light with a single color or single wavelength, like only yellow or only green or red. So those lights are monochromatic light, they have only one color. But polychromatic light is a light with number of colors. So that means it may be, that is the white light. White light has 7 colors, we already know. So it is a polychromatic light. Okay, so when a polychromatic light actually, we already knew about these things. The refractive index light is actually dependent on the wavelength, and it is almost inversely proportional to wavelength. There is 1 upon lambda. Okay, so that means the wavelength of the light higher, the refractive index that it will show of the medium will be smaller. That means if lambda goes high, mu will go down. Okay, so that means wavelength, as we know, the wavelength of red light is higher with this compared to the wavelength of violet light. That means when red light enters to a medium, it will see comparatively lesser refractive index, since it is inversely proportional. If wavelength increases, refractive index decreases. So that means refractive index for red light, that is mu red, is lesser than the refractive index of the violet light, that is for mu of violet. Okay, so that is the idea behind the dispersion. So when polychromatic light incident, like white light, there is 7 colors within it. So the 7 color individually see different amount of refractive index of this medium, of the same medium. Okay, so white light has already 7 colors. Violet color seeing this medium with some amount of refractive index. Red light is seeing that the same medium with a different refractive index. So as a whole, violet color will refract it with some amount of angle, red color of light will diffract it with a different amount of angle, and the rest of the color will be refracted with a different amount of angle. And we can expect the refractive index for the red light is small, so that means red light will not deviate more. Okay, but the violet light has the higher refractive index, so it will bend more. Okay, so when white light incident on a prism, the outcome will be a colored spectrum. Okay, on top of which there will be a red light, since red color will suffer a less amount of deviation, since it is seeing a smaller refractive index of the medium, since it has a higher wavelength. And the violet color of light, it will deviate more, since it is seeing a larger amount of refractive index of the same medium, since it has a smaller wavelength, according to this theorem. This is called the Cauchy's theorem. Okay, so what is dispersion? Dispersion is a phenomena where white light actually divided in its color when it passes through a prism. Okay, so that is the called dispersion. Now first, Newton, Sir Isaac Newton, used the prism to show the dispersion. Okay, now we can use two similar type of prism, but one is straight and another one is upside down. To correct this dispersion, that now put white light here, so it will divide it into 7 colors. These 7 colors will be inserted in the second prism and they will be connected, they will be joined again, and white light will come out from the second prism. Okay, so this is how we can actually uh, mitigate the dispersion, or we can recombine the spectrum again, and this is called spectrum. So this set of color is called spectrum. Okay, so what is dispersion? Dispersion is a phenomena where light, a polychromatic light, actually divided into its constituent colors, and this set of colors are called spectrum. Okay, so this is your spectrum, this is your spectrum. Okay, fine. So this is all about the dispersion. Now we will learn about some physical phenomena or some practical phenomena of this dispersion. Now when we are talking about dispersion, how we can forget about the rainbow? Okay, so that is a complete that is a pure natural example of dispersion of light. Okay, where sunlight, that is a polychromatic white light, that actually falls on the water bubbles or water vapor or water molecules present in the air. Oh sorry, water droplets, not molecules. Those are the water droplets present in the air, and these droplets actually acts like a prism. Okay, where when light incident on this droplet, they divided or they separated or they divided into their constituent colors. Okay, and then they suffers a total internal reflection from the back of this uh, spherical droplet, and when they come out, they divide it into constituent colors, and this actually spectrum is looked by human eye. Okay, and this actually is being looked by human eye. So when actually white light is white light is actually incidenting on water droplet, but the ray that is coming out is a, so I have just showing here I have shown here only the 3 colors. Actually there are 7 colors, but there will be very messy figure, so that's why I actually leave the rest of the colors. So just I have shown violet, yellow and red. Okay, 3 colors I have shown. So when the actual holy white light actually incident on the spherical droplet, and when they comes out, they are divided into their spectrum. Okay, so we can see the colored spectrum, and that is called the rainbow. Okay, so and the one thing we have to keep in mind, the without the water droplet, rainbow cannot be formed. So that's the reason always rainbow forms in the opposite side of the sun. That means if your sun is already in the west, so rainbow will form in the east. Okay, so that's the reason, because some water droplet, since it actually working on the principle of total internal reflection and dispersion uh, as a well. Okay, so that means if light incident from here, that means it is already sun at sun is actually going to set, that means it is at west. Then this water droplet, that means cloud, is at east, so that light actually falling on this thing and you will get the rainbow. Okay, so that is the thing. Next we will learn about the atmospheric refraction. So atmospheric refraction means the refraction from the atmosphere of the earth. So as we know, we already have, that means earth already have a belt of atmosphere around it. Okay, so the light coming from the outside of the earth, that has to suffer some amount of refraction in this atmosphere, and then it will come to our eyes. Okay, so first of all, twinkling of a star, that can be explained on contrast of atmospheric refraction. Now we can understand there are different layers in the atmosphere. Okay, starting from the troposphere, then stratosphere, then ozonosphere or ionosphere, then ionosphere, magnetosphere, mesosphere, exosphere. There are lots of different level of the atmosphere. So we can consider this atmosphere as combination of number of layers present in it. Okay, and as we can understand, the layer very close to the earth has the higher density. So this is more denser than this one, and this is more denser than this one. So as you go out, you will see the density of the layers are falling. That means as you go out, you will get the rarer medium. Okay, so light, when light from comes from the star, it when it encounters the atmosphere of earth, it actually suffers some amount of refraction. Okay, so it as it comes closer to the earth, it actually going from rarer medium to the denser medium. So it will take this kind of path. It will move towards the normal, and it will take this kind of path. Okay, so when you are looking from here, you will not find this path. You actually, our human eye has a limitation. It can't see any object in a curved path. Okay, so it always can see anything in a straight line. So you will see the star here. Okay, you will see the star here. Now uh, problem is that this atmosphere of earth is not fixed always. Okay, this atmosphere of earth is not fixed always, rather it is changing with time. Okay, like there may be some clouds or maybe clear eyes. Sometimes there are no clouds on the sky, that means clear sky. Or sometimes there some amount of cloud comes. Okay, so that means that's how this atmosphere always changes. So that means the density of the these layers are always changing, they keeps on changing. So once this ray coming from the star takes this path, it's uh, you can't guarantee it that the second time this ray will take the similar path. So it can happen second time this ray can take this path as well. Okay, so maybe this path. Okay, so just I am showing one ray of light. There are billions of rays of light, okay, coming from that star, or million rays of light, not billion. Okay, that may be million or billion. That not a countable thing at all. So we are talking about billion number of things. So that means it is possible, with the billion number of rays of light, 100 rays is coming to my eyes now. Now due to change in the atmosphere, uh, due to the change in the atmosphere on the path of this ray, uh, now most of the rays has changed its path, and now 10 number of rays is coming to my eyes. Okay, again the path is cleared, and again the total 100 number of rays is again coming to my eyes. So what is changing, that is number of rays those are coming to my eyes is changing with time, and the number of rays is directly related to the intensity that we are seeing. So that means with the 100 rays we are seeing a brighter one, with 10 rays we are seeing a dimmer one. That means the intensity of the star is continuously fluctuating due to the changing number of rays those are coming to our eyes. Okay, so that is the reason of the twinkling of eyes, sorry, not eyes, twinkling of stars. Okay, so another example or another effect of the atmospheric refraction is the advanced sunrise or delayed sunrise. Now when we are saying the sun is set or sun is rise, when it comes above the uh, when it comes above the horizon. Okay, so now we will take an example where still sun is below the horizon. Okay, now this ray of light, some ray of light has incident here like that. Okay, so this is your rarer medium and this one is your denser medium. So light will move towards the normal, it will come like that. Again, at that interface, this one is rarer, this one is denser, it will bend again towards the normal, and again this one is rarer, this one is denser, so it will bend again towards the normal. So when sun is still below the horizon, you are getting a light from the sun, and exactly you will not going to see this curved path of the light. You will feel the sun is here. Okay, sun is here, so there is a virtual image of the sun that is created due to this refraction. Still the sun is below the horizon, but you are getting the image, you are getting the light from the sun due to the atmospheric refraction. This is so you actually that will be a sunrise for you, or that will not be a sunset for you, but still sun is below the horizon. Okay, so this is the advanced sunrise or delayed sunrise, delayed sunset that I have explained here, that is mainly due to the atmospheric refraction. So last topic of today's discussion is scattering of light. Now what is scattering of light? Scattering of light is mainly uh, absorption and re-emission. Now when there are small particles in the path of the rays of light, so these small particles actually absorb the rays and then re-emit them. Now here I have shown as example. So this is the parallel rays coming from the sun, and here a small particle present in the atmosphere. So what happening to this particle? This particle is taking these parallel rays, absorbing them, and now when it again re-emits them, it actually re-emitting this rays in all possible direction, and this phenomena is called scattering. Okay, so this phenomena is called scattering. So due to this scattering, we know of effect called Tyndall effect. Okay, where we know the atmosphere is full of dust and the small particles suspended in it everywhere. Okay, so when actually rays of light are not visible, since any kind of source of energy is not visible, so rays of light are not visible. But when rays of light travels in a black room or in a dusty room, so we actually can see the exact path of the ray. Actually we are not seeing the path of the ray, actually we are seeing the particles or the dust particle, those are present in the path of the rays. Okay, so the dust particles present in the path of the ray, those particles are taking the rays, that means they are absorbing the rays and they are re-emitting the rays in all possible directions. So we can see them from any direction. Okay, but it will not be possible to see those rays, those parallel rays from any direction, if those particles were not there. Okay, so that is the thing that is called the Tyndall effect, when we actually can see the path of the rays. And same thing happens with the, okay, again one thing I have to mention here, that is the scattering. amount of scattering is proportional to 1 by lambda to the power 4. That is, the lambda is your wavelength. Okay, so that means it actually give you a brief idea about the scattering. That means the lower the wavelength you have, that means your light have, that light will be scattered more. 1 by lambda to the power 4, it is one kind of inversely proportional. So that means lower you have the wavelength of your light, that light will be scattered more. That means red light will scatter less, that will not going to scatter, that means going not going to be re-emitted in all, it not going to scatter in all direction, it always will like to go in its own direction. Okay, so that is the scattering. So that is the reason behind the using of red light in the danger signal. Okay, so red light with higher wavelength, it will not going to scatter, so it will go a large distance, it will travel a large distance, and that signal will be seen from a very large distance. That's all. So red signal will be visible from a large distance. Okay, since this red color of light will not going to have much scattering. Okay, now again there is a two phenomena. One is blue sky, another one is red color of sky during sunrise and sunset. So what is the reason behind the blue sky? Again, blue and violet, these two ray of light has the smallest wavelength. Okay, in white light there are seven colors of light present in the white light, and among them the blue and the violet has the smallest wavelength. Now with the smallest wavelength, they suffers a larger amount of scattering. Okay, so when light comes from the sun, this blue and violet color actually scattered more, and they actually, when light from the sun comes from here, so actually this blue and violet light actually scattered more. Okay, so this blue and violet light can be seen from everywhere on the earth. So it is clear why we can see the sky always blue, or that means always blue. Okay, so since only this violet or blue color is visible, okay, from everywhere. Okay, if we don't had any kind of atmosphere, then there would not be any kind of scattering, so the sky would be black. Okay, the sky would be black. Okay, so so that actually is seen from any flight that is very high, or any satellite, not satellite, we can say spacecraft. Okay, that will be better word to be used. So from a spacecraft, the sky always seen is black. If you look at a picture taken from the moon, the sky is actually seen black there, because there is no atmosphere, there will not be any scattering of light, so there not be any clear visibility, there will not be any light that will come to your eyes directly. Okay, so from the sky. Okay, so light that will come directly from the sun. Okay, so the light that is coming directly from the sun, when you are looking at the sun, take you will get the light. When you are not looking towards the sun, you will not going to get any light, you will see the sky black. Okay, so when you are not looking at the sun, since you are seeing the sky blue, that means some amount of light is coming from the sky, and that is only possible due to the scattering. Okay, and that means the blue sky is already explained here. Now another thing is the red sky during the sunrise or sunset. Now same thing happens for sunrise or sunset, where the sun is on the horizon. So just this thing that means advanced sunrise or delayed sunset, this thing, just forget this thing. We are assuming that the sun is on the horizon. So just without taking consideration of the atmospheric refraction, we just considering that the light is coming directly, that means coming straight towards our eyes, coming straight towards our eyes. Okay, so for that case, now sun is here. If sun comes to here, that means at the mid of the day, again this ray is coming directly from here. Now for this case, this ray is traveling a smaller distance through the atmosphere, but for this, during sunrise or during sunset, this ray is traveling a very large distance through this medium, through this atmosphere. Now if a ray traveling through a medium, that means it will it will be scattered. The more it goes inside that medium, it will scatter more. Okay, so that means with the large amount of length, when the white light actually travels, since we know the blue and the violet colors has a very big amount of scattering, so from this white ray, almost all amount of almost this violet and this violet and blue colors scattered almost completely. That means they actually scattered everywhere. So only the red and the orange, the higher wavelength rays, they actually can continue to the journey to our eye without being scattered. Okay, so that's why we actually see the we actually see the red sky during the sunrise or sunset. Okay, so I think this thing is clear. So this is whole chapter that we all covered in today's class, so that's why this lecture becomes so big. Okay, so thank you very much.